In this video, we're going to be doing a Unit 4 Linear Momentum AP Physics 1 FRQ. Let's say we have a low-friction horizontal track that contains 3 carts. Cart A has a mass m, cart B has a mass 2m, and cart C has a mass 3m. Initially, carts A and B are connected by a compressed ideal spring and are held at rest. Cart C is at rest at a distance L to the right of cart B. At t is equal to 0, the latch moving, the spring is released. The spring pushes carts A and B apart, and cart A moves to the left with speed v initial, while cart B moves to the right toward cart C. Cart B then collides with cart C, and the collision between B and C is perfectly inelastic, so they stick together. After sticking, the combined object BC moves to the right and compresses a horizontal spring of spring constant K, which is attached to a rigid wall. Assume the track is frictionless unless otherwise stated. Using Newton's laws, prove the total momentum of the A and B system is conserved during the spring release. So, in general, we know that our total momentum is equal to the summation of our masses times our velocities. So we know that we are going to have delta P conserved when we have no net external impulse on the system, where we say that our impulse is equal to the change in our system's momentum. And as an extension, this can be represented external as the integral of f external dt. So we know that if that f net external is equal to 0, then that's how we know that the summation of the system is equal to 0. So that means that we could define P initial is equal to P final. So this situation, we're going to define our positive direction as to the right. So we're going to prove conservation. We know that our force on cart A, let's represent this as the force of cart A on the spring, or the spring on cart A as F the spring on A, and then F the spring on B is going to be the spring on cart B. So then if we use Newton's third law, we know that these forces are going to be equal in magnitude, and then they're going to be opposite in their direction, which means that the force of the spring on A is equal to the negative force of the spring on B. So then if we use Newton's second law on each of these carts, we have for cart A, the force of the spring on A is equal to the mass of A times the acceleration of A. And then for B, we have the force of the spring on B is equal to the mass of B times the acceleration of the B. So now we can add these two force equations. We're going to have the force of the spring on A plus the force of the spring on B is equal to the mass of A, acceleration A, mass B, acceleration B. And that's because, again, we have this relationship here. Now, after this, we're going to get that force of spring on A plus the force of spring on B is equal to 0. So that means that mass of A times acceleration of A plus mass of B times acceleration of B is equal to 0. So then we know that acceleration is going to be the derivative of our velocity. So you could also represent this as ma dva over dt plus mb dvb over dt is equal to 0. This is actually extension, but we can do it anyways. ma va mb vb is equal to 0. But we know that this is equal to the total momentum. So then this is equal to 0. Therefore, your total momentum is going to be constant, aka A on B initial is equal to A on B final. So we showed that from F is equal to ma that we have this expression here. So we have F A on B is equal to negative F B on A. Now, find the speed of cart B immediately after the spring release in terms of V initial, we know that initially VA is going to be at rest, cart A is at rest, and B is going to be at rest too initially. So after release, you're going to have cart A move with V initial. But it's going to the left. And then VB is going to be unknown. So we have always MA and then MB. So M and 2M. So we can set them equal and then just solve. So that's 0, MA, VA, MB, VB. So now we just substitute in. We have M times negative V initial plus 2M VB. This is 0, negative MV initial plus 2M VB. Add to both sides, we have MV initial, 2M VB. We have VB is equal to V initial over 2. So now we see that this is going to be a positive number. So that means that cart B is going to move to the right. So cart B does not have the same speed as cart A. Just because you have Newton's third law and you have equal and opposite forces, that does not mean equal speeds, because they have different masses. And since cart B has twice the mass of cart A, it gets half the speed of cart A. So now you could also do this shortcut. Because we know that MA/VA is equal to negative MB/VB, MV initial is equal to 2MVB. So VB is equal to V initial divided by 2. Now, for our next question, we have find the initial elastic potential energy stored in the compressed spring before the release in terms of M and V initial. So what we know is that our spring energy is going to turn into kinetic energy of our carts A and our cart B. So we have a frictionless track, so mu is equal to 0. And also we have an ideal spring. So we have all the things for energy conservation. Now we know initially the system is at rest, right? So that means that kinetic energy initial is equal to 0. So your potential energy, and we have kinetic energy and potential energy. So we are only going to have spring energy here initially. Now, in the end, we know after we have finished, the spring is no longer compressed. No more compression. So that means your spring potential energy is 0. So then we know our final, we're going to have the kinetic energy of both A and kinetic energy of B. So that means that we have that. Now we know kinetic energy is 1/2 mv squared. So for A, we have 1/2 m times VA was V initial squared. And then we have, for B, we have 1/2 2m V initial over 2 squared that we got earlier. So this is going to be 1/2 2m V initial squared over 4. And then we have 1/4 for here, and then divide that by 2, 1/4 m V initial squared. So then after this, we just have 1/2 m V initial squared. So then we can see that we have a fraction we can add. We have 3/4 mv initial squared is equal to the initial spring energy. So our spring energy is not just the kinetic energy of cart A, it becomes the kinetic energy of both our carts. Now, for our next question, find the speed of the combined object BC immediately after the perfectly inelastic collision. Well, we know that B is going to collide with C. So you're going to have, before your collision, the mass of B is equal to 2m, and VB is equal to V initial over 2. And we know that also cart C was equal to 3m, and it was initially at rest. So then we know that after we have that stick, the perfectly inelastic collision. So then we have a combined mass now. We have MB plus MC, which is 2m plus 3m, which is 5m. And then VBC is going to be our final speed. So we are going to have also a short collision. So we know that we have F delta T. So if we have a short collision, the change is going to be negligible. So we are going to have our external impulse in the horizontal direction is going to be negligible. So that is how we can say that we have our conservation of momentum. So we have these equal to each other. Initially, we have MBVB plus MCVC. Finally, we have MB plus MC times VBC. So we can substitute in. Here we are going to have this cancels out, so we have V initial there, and we have 0 here. Then we have 5mVBC. So we're going to get BC is equal to V initial over 5. So this is our answer. So we do not have conservation of energy, so we can't use that, because a perfectly inelastic collision means kinetic energy is not conserved. But remember, with all collisions, we always have conservation of momentum because of that short time that the collision occurs over. Now we can also use a shortcut for this, by the way. So the shortcut is that if you have a stick collision with one object initially at rest, you have VF is equal to M1 over M1 plus M2 times V1. So then you just substitute in like we did here. We had 2m over 5m as our combined mass, and then we have V initial over 2. So then we just have 2 over 2. You just get V initial over 5 is equal to your final. So that's pretty quick. Now, find the fraction of kinetic energy lost during the collision between B and C. So we know that before our collision, we only had cart B moving because cart A was at rest. So then we can write kinetic energy initial 1/2 MBVB squared. So this is going to be canceling out, or we can substitute in 1/2 2m. We have V initial over 2, and we have 1/2, or we can cancel out this 2. So then we know that after the collision, they move together. So we have 1/2 MB plus MC times VBC squared. This is 1/2 times 5m times V initial over 5 squared. So then for the velocity, this is v initial squared over 25. And we have 1/2 times 5m. So this is equal to 5m v initial squared over 50. And we have 1/10m v initial squared. So then we can find our energy loss, because this is going to be the change in kinetic energy. We have initial minus final. That's 1/4 mv initial squared minus 1/10 mv initial squared. Well, 1/4 is same thing as 5/20, and 1/10 is the same thing as 2/20. So you can subtract those and you get 3/20 mv initial squared is going to be the change in kinetic energy that we lost. So then in order to find the fraction that we lost, you have to take the original, or you take k initial over kf, the difference, which was your delta k, right? And then you divide that by your initial. So that was 3/20 mv initial squared divided by 1/4 mv initial squared. Everything cancels out, that is the same. So you just have this 3/2 times 4, because we take the reciprocal. And this is the same thing as 12/20. And you can divide both by a common factor. We can get 3/5 by dividing both by 4. So the fraction of energy loss is 3/5, aka 60% of energy lost. And that kinetic energy is destroyed. It becomes thermal energy or sound or deformation. All of it becomes internal energy lost to another system. So what we saw here is delta P conserved. Kinetic energy not conserved. So we can also do a shortcut for this. Again, we know that we're finding the ratio of the two over the initial. So we have m1 plus m2. So you have 2m over 2m plus 3m. And we get 2/5. So then to find the fraction lost, it's just going to be 1 minus 2/5, aka 3/5. Now find the max compression, x max, of the wall in terms of mv initial and k. So we know after our collision, we have BC is our combined object, right? And it moves together with the speed VBC is equal to V initial over 5. So our combined mass is 5m, which we saw earlier. And we know that it's going to compress the spring until it momentarily stops. So then when you're at your maximum compression, you're going to have that V is equal to 0. So all your kinetic energy becomes your spring potential energy. So then we know that the energy before collision or before compression, that is equal to KBC. And then finally, we had that it's equal to US. So let's set them equal. So we have initial and we have final. We have K, BC, we have US. So let's move this over here. We have 1/2 mVBC squared, 1/2 kx squared max. You get 1/2 5m v initial over 5 squared is 1/2 kx max squared. Velocity, yeah, that's gonna be v initial squared over 25. And this is equal to the same thing, 1/2 kx max squared, 1/2 times 5m. And on the left side, we can simplify this to 5m v initial squared over, this becomes 50. So you have 5m v initial squared all divided by 50 is equal to 1/2 kx maximum squared. Then you have canceled that 5m v initial squared is equal to 1/2 kx maximum squared all divided by 10, or all divided by 10. So then you can multiply both sides here by 2. Then you can cancel that out. You get 2 over 10. But 2 over 10 is the same thing as 1 over 5, right? So then you have m v initial squared over 5, and that's going to be 5. But you can also see here, you can divide k at the same time. Kill two birds with one stone. And you have k here. So then you have x squared max. And then you can take the square root of both sides here. You get x max is equal to v initial, which you can take out because you have a square, times the root of m over 5k. So we have a positive distance that we are going to be compressing. So our compression is a positive distance. X max is equal to this expression. So you have to use kinetic energy after the inelastic collision. So kinetic energy after inelastic collision. So after that part is over. But for the collision, inelastic collision, you can't use kinetic energy because it's not going to be conserved. So a shortcut here we could have used is, we know that 1 kf was equal to 1 over 10 mv initial squared after the collision. So we know that 1 over 10 mv initial squared is equal to 1/2 kx squared. So x is equal to v initial root of m over 5k. Now suppose the track between cart C and the wall spring has kinetic friction UK. The combined BC object moves a distance d after the collision before reaching the wall spring and then compresses the spring by a distance x. Find the equation for the maximum compression x max. You don't need to solve the quadratic fully. So we know that our combined mass, 5m VBC, this is after our collision, is equal to v initial over 5. Kinetic energy initial, 1/2 5m times v initial over 5 squared, or after the collision. All this is after the collision. So we also know that our combined object, it slides d before touching the spring. Then it compresses spring by x max distance. So we know that our total distance over which the spring acts, that's equal to d plus x max. So then our frictional force, mu k times n. We have our horizontal surface, right? So you have a normal force up, mg down, and that's at the center of mass. You have no vertical acceleration because ay is equal to 0, and fn minus mg, that's equal to 0. So fn is equal to mg, which is why we replace it here. So you get mu k m times g. So we know that m is equal to 5m. So you get mu k times 5m times g. 5 mu k mg. Work done by friction, negative FK d plus x max. That's equal to negative 5 mu k mg d plus x max. And then we have energy with non-conservative work. So this is equal to your final energy. So we can use our initial energy. So initially we have this is equal to kinetic initial. And then finally we have this is equal to spring. So we substitute in everything. And then here we substitute in our expression. So this is our equation for our max compression. So this is going to be a quadratic. So if we want to put this in our standard quadratic form, you can just move everything to one side. That's all equal to 0. So an important thing you have to realize is that the object is only going to reach the spring if it still has kinetic energy after it travels the distance d. So our energy lost to friction before reaching the spring, that is going to be work friction is 5 mu k mgd. So our spring, it only reaches our spring if we have 1 over 10 mv initial squared is greater than 5 mu k mg times d. So you cancel m. Your condition is now this. Then you can multiply both sides by 10. So that's true. So if this is not true, then object stops before reaching the spring. So explain why our momentum is conserved during the BC collision, but not the mechanical energy. The reason is because the cards are going to stick together. So that means some of that kinetic energy is becoming internal, thermal, sound, and deformation. So again, our momentum conservation, it depends on our external impulse, and our energy conservation, it depends whether or not we have non-conservative processes that transform our mechanical energy into internal energy. So our sticky collision, it's able to conserve momentum, but also it loses kinetic energy.